Okay, hi everyone. We're going to go ahead and get started. This is a joint M-Cubed and RAL seminar, and I'm pleased to present Erin Dougherty. I think I said that right. Dougherty. Okay, I was very wrong, I guess. Erin is a project scientist in RAL where she uses convection-permitting models and wharf hydro to study changes to the hydrological cycle due to cloud seeding and climate change. Prior to her current position, Erin received a PhD from Colorado State, working with Dr. Kristen Rasmussen on future changes to flood-producing storms. After her PhD, Erin was an ASP postdoc in RAL, where she investigated the connection between floods and storm types, as well as future changes to MCSs. Welcome.
Thank you. Thanks everyone for showing up today. So I'm going to be discussing future changes to weather systems in both the US and Africa using convection-permitting simulations. And before I get started, I just wanted to thank all my co-authors who made this work possible. So the outline of the talk is split into two different sections, focusing on two different studies. So the first part, I will talk about future changes to central US MCS rainfall caused by changes in convective and stratiform structure. The second part will look over Africa to study changes to the weather climate system using PGW simulations in a convection-permitting model. So starting first with future MCS rainfall, this is work that I did during my ASP postdoc with the co-authors listed here. This is in JGR atmosphere, so if you have more questions or want to go into more detail, you can read the paper there. So I focused on the central United States because it is a really flash flood prone region. It's mainly due to organized summertime storms known as mesoscale convective systems, which you can see here. This is a radar image. Sorry, let me get the laser pointer. Here we go. So this is just a radar screenshot that I took on my phone during the Pecan Field campaign. You can see these are really large organized systems of convection with pretty intense rainfall, usually followed by some lighter stratiform rainfall. And they're really beneficial because they do provide 30 to 70% of the warm season rainfall in the central US, but they're also detrimental in producing flash floods. So this figure is from a study I did during my PhD where I compiled a flood-producing storm database. So I basically took flood storm reports along with streamflow indicated floods and stage 4 rainfall to look at the properties of different types of flood-producing storms. So what this image is showing is the frequency of flash flood rainfall, and you can see that it maximizes over the central US here. So that's motivation for why we want to study this region. So the big question is, how will climate change affect these storms? There have been a number of studies that have looked at this before, mainly using convection-permitting models. So this is a study from Rasmussen et al. In 2020, and they looked at changes to storm types and the storm environment. So they found in this top figure here that there's an increase in convective available potential energy due to increases in low-level moisture. And they also found an increase in the convective inhibition, as shown here in the bottom panel. And so what that resulted in, when looking at future projections of these storms, was an increased frequency of really strong, vigorous storms and a decreased frequency of weaker storms due to the fact that you have an increase in SIN. Andreas has obviously done a lot of work in this area too, and using the same set of simulations, so the CONUS-1 simulations, if you're familiar with those, he found, and other co-authors, that by the end of century, there will be an increase in MCS rainfall, rain rate, and the rainfall area. However, both of these studies are just using one deterministic run in both the control and future climate. So a big question I had during my ASP postdoc is not only what is driving this future rainfall change, but what is the uncertainty when we look at an ensemble of convection-permitting models. So that was the goal of the research, analyzing future rainfall changes from flood-producing MCSs, using ensemble simulations to study that variability in future MCS rainfall and then also the structure. So in order to do this, I looked at 8 MCS cases. These cases are taken from that flood-producing storm database that I created during my PhD. And so these episode ideas, they relate to the NCI storm events database. And then what you see here, these dots are showing that centroid location of all the flash flood reports associated with that particular MCS. You can see they're all in June to basically keep the large-scale forcing at rates somewhat similar. And I looked at different MCS types. And so these MCS types are from prior research that's looking at basically the configuration of convective and stratiform regions. So you can see all of these different MCS types are listed here. There's even some that are nonlinear that I haven't listed. But basically it's showing, as an example, this is a trailing line adjoining stratiform type of MCS, where you have this leading line of convection followed by this trailing stratiform area. And this type of MCS tends to move parallel to some sort of boundary. So that just gives you an example of one of those types, but we're examining a number of different types because we're looking at the structural changes within the MCSs. In order to model these, I used WRF, and I simulated these 8 MCSs in a current climate. And I used an ensemble of simulations in a current climate forced by ERA5 reanalysis data. In order to capture the historical variability, I also added this perturbation from the ERA5 reanalysis. They have 10 ensemble members. So I basically took the difference between each ensemble member minus the ERA5 deterministic and added that to the original ERA5. The reason why I didn't directly downscale each ensemble member is because they're 60-kilometer grid spacing and 3 hourly, so they're much too coarse to directly downscale to look at MCSs. So we essentially have each of those 8 MCSs times 11 of those ensemble members, so we have 88 realizations of those storms in a historical climate. I also used a future climate simulation. In this sense, I'm using the pseudo-global warming, or PGW approach. Again, this is being forced by the ERA5 reanalysis data, but now I'm adding a delta signal. And this delta signal is from CSM lens. And so from lens, I'm taking a future period. So in this case, it's mid-century from 2050 to 2080, and subtracting a historical period, which I'm using 1975 to 2005. And we're using ensembles in the PGW framework as well. So I'm using 13 of the 40 lens ensemble members to capture the future variability in these 8 MCSs. These are the WRF domains I used. I had a northern and southern domain. The reason why I was split into 2 is just to increase the computational efficiency, since I am running ensemble members at convection-permitting scales. So I used 3-kilometer grid spacing, which does pretty well in capturing some of those mesoscale features. So you might be wondering, what does this future delta forcing look like? These are basically the different variables that were perturbed as a function of pressure over the central United States. And yeah, so we have 13 ensemble members times 8 MCSs. There's 104 future simulations. So the ensemble mean is shown in dark blue here, and each individual ensemble member is shown in light blue. So you can see for some variables, like temperature here, the ensemble members tend to agree on what that future change is. So in the central United States, is about a warming signal of 4 degrees Kelvin. However, there's some other variables, particularly specific humidity and the UNV winds, where you see a lot more variation in the ensemble member spread. So that really points to the need to incorporate these ensemble simulations for future projections in order to capture that uncertainty. And then looking at the forcings a different way, these are maps of different variables over the central United States. So you can see that obviously there's increase in temperature at the low level, so around 4 degrees Kelvin. We also see an increase in the mixing ratio, so about 2 grams per kilogram. And then I also looked at the change in the vertical wind shear, since that's really important for dictating MCS behavior and longevity. So in this case, it's about a decrease in vertical wind shear of 2 meters per second. And so essentially what these simulations are doing from the PGW is they're looking at these MCSs in a warmer, moister environment, and then you're keeping the large-scale synoptic flow largely the same. So the second piece of the methodology was to identify convective and stratiform regions to see how they contribute to changes in rainfall within the MCSs. So this is an example of just one time step from the model output reflectivity of one of the MCSs, and then the convective stratiform partition is shown on the right. And so what I'm identifying is wide convective core regions, so basically anywhere that has 40 dBz over 1,000 square kilometers, a broad stratiform region, which is shown in blue here, and that has between 18 to 40 dBz over 50,000 square kilometers. And then not shown but also identified are deep convective cores. So basically any 3-kilometer grid cell that has at least 40 dBz extending continuously up to or above 10 kilometers in height is a deep convective core. So these definitions are taken from prior literature and applied in this research. So you might be asking, how well does this algorithm do, and how does this compare to observed reflectivity and the convective stratiform partition? So on the top here, we have the control reflectivity, and then on the right is the identification of those convective and stratiform areas. We compared this to the observed reflectivity at the same time for the same storm, although this observed reflectivity is 1 kilometer compared to this 3 kilometers from the control simulation. And then you can see the results of the partitioning on the observations. So you see a pretty common model issue that even at 3 kilometers, we tend to have convective areas that are too large. There's been some prior research that has shown even at convection permitting scales, you're getting updrafts that are too large, which is probably why we're seeing this bias that we see here. And then we also see stratiform areas that are too small. Again, this has been noted as a common issue when working at convection permitting scales. So keep these biases in mind. But overall, it does do a good job of delineating those areas and also comparing well to the intensity and the movement of those MCSs that were observed. So getting into the results now, we looked at the future change in rainfall within each of those 8 MCSs. And so what you're seeing, this is the percent change in the future area average rainfall over the life cycle of these MCSs. So each line is a different MCS, where the dark line is the ensemble mean, and then the shading is representing the standard deviation between the ensemble members. So overall, we see an increase with a 98% increase in area average rainfall. You'll see that there's a large increase at the beginning of the storm's lifetime where maybe you have more deep convective elements, and then it sort of gradually tapers off. We also looked at the change in the maximum hourly rain rates, which does show an increase. So on average, it increases by 31%, but you see a lot more variability in the standard deviation due to the fact that maximum hourly rain rates, it tends to be a noisier field in general. So there's a little bit more uncertainty in what those future changes are. We also looked at changes in the area, since that can contribute to changes in rainfall. So now we're looking at probability density functions for the 8 MCSs. Again, each color shows a different MCS, and each curve is showing the ensemble member spread. So overall, we see an increase of 41% in the MCS size, and you can see there's a lot of variation between the different storms. When we broke this down into the wide convective core area and the broad stratiform region area, we see that this increase in MCS size is largely being driven by an increase in the wide convective core area. So the convective areas are growing larger than the increase in the stratiform areas. We also looked at changes in the number of deep convective cores. Remember, these are just any grid cell that has basically really deep convection. So this is looking at the number, so the absolute change within those 8 MCSs, where the spread is shown by the box plot. So you can see for all MCSs, we see an increase in the deep convective cores. And so I wanted to investigate why that might be. So in order to do that, I looked at changes in the environment before these MCSs developed. And unsurprisingly, the CAPE increases in all the 8 MCSs because we have more low-level moisture. We also looked at changes in SIN as well, which tended to vary. So some MCSs had weaker SIN, some had stronger SIN. And then we looked at changes in the maximum updraft velocity. So if you recall, the 2 storms that had the greatest increase in the number of deep convective cores were this back building and then trailing stratiform number 3, MCS. And those storms had an increase in CAPE and SIN, and we're obviously able to overcome that increase in SIN as evidenced by this increase in updraft velocity. So we think that the change in deep convective cores is because you have not only stronger CAPE, but stronger SIN as well. So finally, I looked at the rainfall changes by the elements of the storm. So deep convective cores, wide convective cores, and broad stratiform regions. So this is a box plot showing the change in the deep convective core max accumulated rainfall. And you see that there's a large increase. So on average, there's an increase of 169%, but there's a ton of variability between the ensemble members. So this suggests that this is a very uncertain future response from the ensemble member spread. In the wide convective cores, we do also see an increase, but you can see the spread between the ensemble members is much smaller. So this is indicating that it's a much more robust future response in that rainfall change. And then broad stratiform region, we see a slight increase with some variability in the ensemble members, but not as much as the deep convective cores. And then the same is true when we look at the area average rainfall. So again, deep convective cores show a large change, but large variability, whereas wide convective cores show a small range and also an increase. What's really interesting, and I would love to look into this more, is the broad stratiform region, the area average rainfall actually decreases in a future climate. So I haven't looked into why that is yet, but I think there could be a lot of interesting things to look into. So in summary, we see that these future MCSs have larger area and they have more convective rainfall. So comparing these two different storms, we see that the larger MCS area is really being driven by an increase in the wide convective core area. The increase in rainfall is mainly driven by those convective areas, so deep convective cores and wide convective cores. And we see a greater variability in the deep convective cores and broad stratiform regions compared to the wide convective cores. So this is really trying to understand what are the sources of uncertainty in future rainfall. So next I'm going to shift gears into a very different part of the world. So this is a study that I'm doing with Kelly Nunez-Ocasio, who's here today as part of her ASP postdoc. And she'll be moving on to Texas A&M soon as a faculty, so hoping to continue some of this research with Kelly soon. So we're focusing on Africa because there's a lot of really interesting processes operating at different scales that lead to tropical cyclogenesis, which is obviously a pretty high impact weather event. So to give you a framework of what we're looking at, the main features over Africa that we are interested in are the African easterly jet, which arises due to the clash of this hot Saharan air with relatively cooler and moister air brought in by the West African monsoon. And so this arises due to thermal wind balance. And then this West African monsoon that provides a source of shear and also moisture for the African easterly waves and MCSs. And these African easterly waves and the MCSs can develop into tropical cyclones. So there's a lot of feedbacks between synoptic and convective scales here. So there's been some studies that have started to look into this region, particularly how this will change in a future and warmer climate. So one study is from Burkos Hickey and Patrick Kola, 2021, that looked at changes in the African easterly jet. So what you see on the left is a historical African easterly jet as a function of latitude over the region. So this is the zonal wind speed. And then on the right is the future African easterly jet. So you can see that the African easterly jet, it shifts northward, according to the study, and actually weakens in a warmer climate. And I should note that they are using PGW simulations, but for both their control and PGW simulations, they're using 27 kilometers, so it is not convection permitting. More recently, there's a study by Haim et al. In 2023. So they used a 3-kilometer model to look at tropical clouds and how they're being represented. So in this case, this is the tropical Atlantic, which includes parts of Western Africa. And they compare that to how well they represent clouds compared to CPMs, and then look at the future changes. So this is showing the tropical cloud albedo as a function of month. And you can see that these 3-kilometer simulations, they tend to better simulate the amplitude and the timing of these tropical clouds compared to CPMs. So I think that motivates the use of convection-permitting models to capture some of these tropical clouds, but also to capture the feedbacks between these convective scale features with some of the larger scale synoptic features like the African easterly jet. And yeah.
It's happening up at 200 millibar.
That's a great question. It looks like a stronger upper level jet in that case. I don't remember if they specifically looked at the tropical easterly jet in this study. I think the main focus was on the African easterly jet, but I know some other work, especially in CGD, was looking at some global changes in the upper level jet and found some strengthening in a warmer climate. So it could be fitting with that, but yeah, I don't recall if they specifically looked into that, but it would fit with some prior research. Yeah, good question. And so getting back to this, we looked at Hurricane Helene. Hurricane Helene is a really nice case study because it presents all these different weather systems that are interacting over Africa to produce a tropical cyclone. So Hurricane Helene developed from an interaction between an African easterly wave and an MCS. So this is just showing an African easterly wave, and then a day later, it basically turns into Hurricane Helene. So there's been prior research from Nunez-Ocasio and Rios-Barrios looking at this pre-Helene environment as it developed from an African easterly wave. So this took place in early September, and then once it reached September 13th, it became a tropical cyclone. So the focus of this research is understanding how does the African weather climate system that supported tropical cyclone genesis in Hurricane Helene, how does that change in a warmer and moister climate using convection-permitting models? So we can fully capture those moisture feedbacks between the varying different scales over Africa. And in this study, we're really just focusing on this pre-Helene period. Future work can look into some changes for the tropical cyclone, but we just want to understand how all of these different features, the MCS, the West African monsoon, ITCZ, how are those all changing in this one really nice case study. So in order to do this, we use MPAS for our simulations. We have 3 spin-up periods to make sure what we're seeing is not just an artifact of spin-up. So essentially we're using September 5th, September 6th, and then September 8th, and we're running it through September 13th, 18 UTC. And the region we're using a limited area domain with this 15 3-kilometer mesh centered basically over Africa. And then you can see we're also capturing parts of the tropical Atlantic as well. So we're also initializing this with ERA5 reanalysis data for both control and PGW experiments. Because we do have 3 kilometers for our inner mesh, we're using the convection-permitting suites in MPAS. So for our experiment design, the control is just forced by ERA5 reanalysis. So this time we just have one deterministic run. And then for the future climate, we're using ERA5 reanalysis plus the delta signal from lens 2. In this case, we're using a delta signal that is representative of the end of century period minus a historical period under SSP 3.7. And we're taking the 100-member ensemble mean. So in this case, we just have deterministic runs for the control climate and for the PGW using 3 different initialization times. To give you a sense of what those delta signals look like that we are adding to the ERA5 reanalysis data, we have the change in temperature shown here over Africa. And in this white box is the West African monsoon region. So you can see there tends to be a lot of warming, especially in the Sahara here, a little bit less over the West African monsoon region. And then when we look at moisture, the main increase is over that monsoonal region, which is unsurprising. To compare MPAS to observations, we have Hofmahler diagrams as a function of longitude on the x-axis and time increasing as you go upwards for both the rain rate and then the relative vorticity and relative humidity. So comparing MPAS, which is on the bottom here, to observations, we see that it compares really nicely, except MPAS tends to have a little bit broader features. So both the rain rate and the relative vorticity are a little bit more covering a broader region compared to observations. But overall, we do see the timing and the magnitude is pretty similar between MPAS and observations. So that gives us confidence in what we're seeing for our results. So getting into the results, we looked at changes in precipitation and moisture over that several-day period leading up to Hurricane Helene. So what we have is the precipitation rate in control, PGW in the middle, and then the difference on the bottom. So overall, we do see an increase in precipitation, especially off the west coast of Africa, and also in the Bight of Benin. So some of those important features are shown up here on the top. And again, you see that box for the West African monsoon region. We also looked at changes in the low-level moisture and winds, which is shown in this plot. And if you look at the difference, you see that there is a pretty significant moisture increase, especially over that West African monsoon region. And then if we just plot the low-level winds by themselves, we can look at some of the changes in magnitude and direction. So we see from the flow, southwesterly flow here, there is a stronger monsoon that's impinging upon the coast. And we also see stronger cyclonic flow offshore, possibly indicating stronger African easterly waves. So if we take an average over that monsoon box here, we're looking at changes in variables as a function of latitude. So we have OLR, precipitable water, and the precipitation rate. And the changes are shown for PGW in orange and control in blue. And so between this box outlined in black here, between -5 to 7, we see that there tends to be deeper convection in the PGW simulations. Precipitable water, that increases across the board due to warmer temperatures. And then when we look at the precipitation rate, we see it's higher, but we also see this notable southward shift as well that matches where we're seeing that deeper convection in PGW. We looked at changes in diabatic heating as well. This is a little bit further region, so we're going from 0 to 30 degrees north here. And so in the control, we see that convection is largely between 5 to 15 degrees north. And then when we look at PGW, we can see that this convection is much deeper, and it tends to be wider in a warmer climate. When we take the difference, we see this intensification of diabatic heating, and we also see a southern shift in that diabatic heating that's consistent with the southern shift in precipitation. So finally, we wanted to understand how does African easterly jet change over this period. And so we have cross-sections of the African easterly jet as a function of latitude. So we're looking at zonal wind speed here, and the African easterly jet is shown around 700 hectopascals. So if we look at the change in the African easterly jet, we do see a northern shift like other studies have found, but we also see an intensification of the jet. And we're still looking into reasons why the African easterly jet is shifting and becoming more intense. And one hypothesis we have is it's due to changes in the meridional temperature gradient. So this is just the delta signal that we add to ERA 5 in the MPAS runs, but we do see there is a pretty strong gradient in temperature shown here. So we're looking into that, but just based on thermal wind arguments, you would expect if there's a stronger temperature gradient, you would have a stronger jet. So the next question we wanted to address with these simulations is how does this affect changes in MCSs over Africa? The reason why is because the interaction between MCSs and African easterly waves can lead to TC genesis. So this is a nice schematic from Nunez-Ocasio et al. In 2020, essentially showing MCSs that turn into a tropical cyclone on the left and those that do not become a tropical cyclone on the right. So essentially what happens if the African easterly wave and MCSs are within phase with one another, that will more favorably lead to tropical cyclogenesis because that MCS is providing diabatic heating and moisture for that wave to develop. Compared to systems that are out of phase, those tend to not lead to tropical cyclogenesis. So the MCSs provide important fuel for tropical cyclones, but also they're high impact weather events that affect people in this region as well. So in order to track these MCSs, we are using TAMS, which is a tracker developed by Nunez-Ocasio and Moon 2024. If you're interested, you can scan the QR code and look into it yourself. I would also say if you have questions about this, I would direct it to Kelly because she's the one who did the tracking. But we used brightness temperature thresholds for tracking. We used 235K for large areas and 219K for the embedded areas. And so we track these MCSs using those same set of simulations that I showed before. So now we are looking at the changes in MCS location over Africa. in those model runs I mentioned before. So the 3 different panels are those 3 different initialization times. PGW MCSs are shown in orange, and the control are shown in blue. We did also track disorganized convection. That's what the D stands for. And then CCC and MCC are MCSs that are, some are circular and some are more linear. So what really jumps out from these results is that you have more MCSs originating over the Indian Ocean. If you look at this as a function of latitude, we also see a southward shift in the MCSs, particularly just below the equator here. Looking at this by a function of longitude, we see more MCSs in the PGW runs tend to occur further east and further west in the future climate. So the further west MCSs could be maybe pre-tropical cyclogenesis events, but we're still looking into that to see what those might be. And then we looked at the properties of the MCSs themselves in a future climate. So this is a 2D histogram of minimum brightness temperature and the median precipitation rate in those MCSs. You can see the distribution to both the top and side of the plot, and you can see a clear shift in heavier precipitation rates in those future MCSs. And there's maybe slightly colder cloud tops, but it's a little bit hard to tell from this plot here. We then wanted to look at changes in updrafts and downdrafts to understand, are these MCSs becoming more intense? What are their dynamics like? And so we looked at the minimum and maximum vertical velocity at 500 hectopascals. And we found, by and large, that the future MCSs have both weaker updrafts and weaker downdrafts in a future climate, which was puzzling to me because we tend to see the opposite in the United States and mid-latitude MCSs. So we're trying to reconcile what we're seeing and connect that back to changes in the African easterly jet. So if you recall, we do see the African easterly jet shifts northward and intensifies in a warmer climate. At the same time, we're seeing a southward shift of the MCSs. So currently, we're hypothesizing that these weaker MCSs could be due to the fact that they have less upper level support from the African easterly jet as it shifts northward, but the increase in rainfall is just due to the fact that you have more moisture in a warmer climate. So to summarize what we found in this study, which I didn't mention, but it is in revision at GRL, and then the MCS part is being worked on now. These are the relevant systems that we looked at over Africa, and the future changes that we're seeing in these PGW experiments are a northern shift of the African easterly jet and an intensification. And at the same time, we're seeing a southern shift in convection and precipitation. And we're also seeing a stronger West African monsoon, which is bringing in more moisture to this area. So I will end with a few remaining questions, since this still is work in progress. So we're still trying to understand why do we see this northern shift of the African easterly jet. We also want to understand how does this pre-tropical cyclogenesis case compare to others? Was Hurricane Helene the pre-environment anomalous, or is this pretty consistent with what we see for other cases? And then what is that interaction between the jet and MCSs in a warmer climate? How do those moisture feedbacks affect the jet and the location and strength of it? And then finally, what we would really love to do is look at this in a full season of simulations, or even multiple years, to just basically make these results more robust and to get more statistics. So I will leave it at that, and I'd be happy to take any questions. Thank you.
Thank you. Plenty of time for questions.
I'll start off. Very, very nice presentation.
Thank you.
One of the clearer presentations I've heard. But I always need clarification with these pseudo-global warming approaches. I've given Andreas a lot of trouble with this. But with pseudo-global warming, you're using the Error 5 analysis and just adding the thermal
Yes.
changes. So in a global warming, you're not considering the possibility of the large-scale pattern changing.
Right. Yes.
And so that, have you thought about how that might affect your results?
Yeah, that is definitely a limitation of the PGW approach. If we considered some of the large-scale changes, you might see maybe a greater migration in, for instance, the African easterly jet. So really what you're seeing for the changes in the jet are just a function of those changes in moisture and temperature. So there could be greater changes, but that, yeah, we obviously can address in PGW simulations.
Yeah, and that would be true for the U.S. as well, right?
Correct. Yeah.
The large-scale pattern may be very different, so, you know, the triggering initiation of convection, you know, there could be differences.
Yeah, absolutely. And I am doing some current research that's using high-resolution CSM lens to directly downscale that so that you could start to get at some of those shifts in the location from the large-scale forcing itself and not be constrained by the PGW method.
Okay, thank you.
Yeah.
Okay. Let's see.
Erin, thanks for that nice talk. And my question goes back to the first part. It looked like there could be a bias in the reflectivity or in the definition of stratiform and convection that I'm wondering how much that bias might be affecting the results you get in the partitioning. And if you can look or just maybe conjecture a bit at, you know, underlying a lot of this is often microphysics and microphysical errors that lead to various problems in representing MCSs. So cold pools sometimes can give you a signal whether there's an aggregate problem with the microphysics, but there may be other things you could look at. I'm wondering if you have, and if that underlies some of the results you're getting for these different definitions as you move to the future, and if some of these things are aggravated a little bit or even worse because of that. Anyway, sorry for the long question.
Yeah, no, that's a fantastic question. So I did look at different thresholds that I used for convective areas and stratiform areas, because those can be very sensitive based on where you are in the globe, right? Tropical versus mid-latitude convection. And overall, I was seeing pretty similar results, but I did not consider different ways or different variables to include within the convective stratiform partition. So I know there's some current research at CSU that's incorporating vertical velocity as a metric to include in the convective stratiform partition. So I did not look at that, but I know from comparing my results with some of the work at CSU that the results are pretty similar, at least within the convective areas having more rainfall and stratiform areas having less in the future. So at least that provides some sanity check for that other people are doing. Yeah, great question.
Since I'm here, just want to comment on that one, the comment that Chris just gave. Because when you have the definition of like certain height, certain area, in the future round, you might actually have cases like just past that threshold that was not there in your historical.
Right.
And suddenly your statistics actually are sampling different things at this way. So can you actually look at those co-located or from based on the historical identified objects and then see their behavior in the future? Because in the future, your populations actually probably change a lot based on that definition.
Yeah, no, that's a really great point. I think that's something that could be incorporated to future work, using maybe more statistical thresholds of these convective stratiform partition that is maybe more representative of this shift in, whoops, I was too excited, shift in the PDF of convective and stratiform areas. So yeah, great comment, thanks.
Fascinating. Thank you very much. One of the things, as a survivor of the gate experiment, I remember one of the things we saw were these big squall lines coming off the African continent with long trailing anvils. The question is, if you do get an increase of this upward easterly jet that Rituna was talking about, would that change those in some fundamental way so that you'd have less stratiform?
That's a great question. Yeah, I haven't looked into that, but it could potentially, I mean, if the jet is stronger, how well would we do in capturing some of those anvils at this resolution? I'm not sure, but yeah, that's a good point. I don't have a good answer for you, but yeah, it's a good area to look into.
Kind of fascinating. Yeah, thank you.
Thanks.
I have a question about the ensembles with the 11 members. Can you get robust results using fewer members potentially? Or conversely, is it enough members to get, like, are the results truly robust? If you had more members, would you get a different spread, for example?
Yeah, so that's actually something I didn't talk about, but I'll show you. There's a lot of ways of basically subsampling ensemble members to make sure you're capturing the full variability. So what I did, I basically took thresholds of the distribution for things like temperature, moisture, and the shear. And I basically took the full members from that full range of distribution. So you're capturing the full range of what CSM Lens is saying. So basically, even though there's 13 ensemble members, the rest of the ensemble members will fall somewhere within there. So ideally, you should be. I don't think necessarily more ensemble members equals more confidence, because depending on the range that you are using. But obviously, it'd be great to use more just for statistical confidence. But I think if you use it in a physically based way, you can be smart about how robust the results are you're getting.
Okay, and potentially fewer too, if you
Yep.
could run more cases, or especially with finer grid spacing, which I'm glad you pointed out the the 3 kilometer grid spacing issues that are out there. Unless someone else, I actually have one completely unrelated question to that. So the weakening of the updrafts for the African MCS is really interesting. I'm guessing you looked at CAPE yet, or have you looked at just changes in CAPE? Are they associated with that?
We're working on that now.
Okay.
Yeah. So hopefully we'll have that result soon.
Yeah, I had a question about that too, because we studied the convective cores in gate, and one of the things restricting their intensity was precipitation. So perhaps more precipitation might be a factor there as well. And if you're counting it in the CAPE, then you're taking care of it.
Right, right. Yeah, thanks for mentioning that.
I related to that. I did notice that in the U.S. MCS changes, that the maximum vertical velocity scaled quite closely with the CAPE, except for the one case, which I think was the third one in. I don't know if you have a comment on that particular case, or maybe why the relationship doesn't hold for that one.
Oh, yeah, let me go back to that plot. Are you referring to this one?
Yes.
Yeah, which case are you referring to?
So it's the
specifically?
third one from the left is the only one that doesn't follow the CAPE goes up by a certain amount and W max goes up. The rest of them really hold really closely with that pattern, except for that one case.
Yeah, so that one, so I do wonder if that could be some of the influence of the large scale as well, if there's more upper level support possibly for that, or depending on, if it's associated with the front. I haven't specifically looked at why that is, but yeah, that's a good point.
All right, any further questions? If not, let's thank the speaker once more.